So in the next half an hour roughly, we're going to try and solve the radiative transfer equation in a very simplified way. Okay? So what you have in the falc.dat file is basically 12 rows, okay, of data. We are only interested in the first or 0th row for C fans, and the third or the second row for people who speak C. So the first one is the log tau, which is the logarithm of the optical depth in the continuum. And the third one is the temperature. We are only going to need these two at the moment, because we're going to do something very, very simplified. And we are going to model the atmosphere, actually not the atmosphere, we're going to solve the radiative transfer equation, assuming that each point, or actually the space between each of the discrete points of the model atmosphere, is a slab with constant properties, okay? So basically these slabs are going to be hotter down there, then colder, then hotter again. Okay, we're going to visualize all this, so I'm going to show you what I mean. And then we're going to assume, and you saw it in Hans' lecture previously, that the intensity in each slab is equal to the intensity in the previous slab, properly attenuated for the absorption in the slab, plus this contribution coming from the source function in the slab, okay? And then we're going to start from the bottom, and we're going to basically integrate in a way going up. And this delta is the monochromatic optical depth between 2 points. And we're going to model it as given optical depth plus some contribution from a line that we're going to make up on the spot. Okay? So those of you who feel confident, you can try and do it on your own. For the other ones, what I'm going to do now is I'm going to open a terminal and an editor, and we're going to go through all these steps together, writing it from scratch. And then you'll see what's happening, okay? I will do it here on my computer. You tell me if it's maybe too small and if I need to zoom the things. So let me go okay, I know where it is on my computer. Make sure that I'm going to do everything in Python. So I hope it's okay for ideal people to at least follow. So what I'm going to do is I'm going to open an IPython and I'm going to zoom this thing a little bit. Like this should be good, I guess. Okay, and what I'm going to do is I'm first going to open the atmospheric file, and we're going to do it like this. Here you put the path where you downloaded it. For me, it's in my folder where I keep stuff like that. Do skip row equals 1 to skip the first row, because that's the way a file is made, and do unpack equals true. Okay. Sorry, you need to import numpy first, and while we are there, let's also import matplotlib pyplot as plt. Okay, so now we can do this. Okay, skip rows maybe. Yeah, skip rows. Okay. And when you look at Atmos, I love to do this shape for everything that I do to make sure that everything is good. You'll see that it's a 2D array. 12 times 57. 12 is for different atmospheric parameters that we use to describe the atmosphere, and here we use only index 0 and index 2. 57 is number of depth points. So to convince you that this is really true, what I'm going to do is I'm going to open another window with some plots. And I'm going to do a plot of Atmos 0 as x coordinate, Atmos 2 as y coordinate, and it looks like this. Okay, so this is the photosphere here. So this is log tau. Okay, this is the temperature. This is the photosphere. Left is the chromosphere and the corona. So we see what we talked about before. This is a mean model of solar atmosphere, one of the mean models. The temperature goes down, reaches the temperature minimum, and then we go up. And then we're going to try to model how the line would form in here. Okay. So for that, I'm going to actually open an editor and go with you through a file that we can work on together. It's where is it? Where is it now? Actually, let's just write it together. Okay. So I'm going to exit this. Going to open Sublime. Let's say whatever you want to do. Formal solution .py. I'm going to zoom this one as well. No, it works differently. This is big enough, I guess. Okay, So let's import matplotlib, pyplot, sblt. Let's import numpy, xmp. Import sys allows you to provide arguments in the console, so we can change the file that we are inputting. Okay, and let's say that file name is sys1. Okay, and then first thing that we're going to do in our code is we're going to load the Atmos. And we said unpack equals true. Okay, these things are going to look a little bit ugly, so tell me to shift if I need to do something. Okay, cool. And then for easier notation, we're going to say like this. Tau continuum is mp copy Atmos 0, and temperature is mp copy Atmos 2. So we have these two things separated here. But be aware that tau is actually log tau, so we want to change it, right? Using something like this. Cool? And we want to turn temperature in the source function, right? So then before that we need to choose what we want to do. And we're not going to work with real spectral lines and actually calculate all the opacities and emissivities because it's a lot of work. People spend significant amounts of their lives deriving codes that use the atomic data which is provided to calculate these things. So we're going to do something ad hoc. Let's say that we are developing a simplified model for, let's say, 6301.5 line of Hinode. So we can use that as our central wavelength. And I'm going to do a thing that you probably hate a lot, but we are used to that. I'm going to work in CGS units. So that's really despicable, I know, but what can we do? So this is in angstrom. To go from angstrom to centimeters, I need to divide this by 1e to minus 8. Okay? So then let's go and calculate the source function for this line. So for that, I'm going to need some constants. I know I could get them from SciPy, but it's actually easier to type them on my own. So, and also if you happen to miss them sometimes, these are the values from for Planck constant, Boltzmann constant, and speed of light. So now we can calculate the source function, and the source function is going to be what? 2 times h times c squared over lambda 0 to 5 times, what was it? Actually divided by mp/exp h times c divided by lambda 0 divided by k divided by t minus 1, right? So this is already a good moment to run our code and see if this works as it should. So I'm going to run IPython again. I'm going to go run formal solution and the path to my atmospheric file, right? And it is this. And correct me in real time if I write something wrong, please. A lot of you know Python much better than I do. No, sir.
Planck's constant is wrong.
Huh? What? My Planck constant is wrong. 6.626 times 10 to the minus 23. 27. Yes, thank you. You're right. Yeah. Okay, this does something. Let's plot. So the obvious thing to try now would be this, right? Actually, I first need the interactive plotting window. Something like this. Nice. And be very careful what your units are. Before, if we were to do like this now, sorry, we would get a completely meaningless graph. Why is this like this? Can somebody tell me? So I plotted source function versus the optical depth, and it looks really weird. Why? Because we want the log scale, right? The optical depth is very tricky unit in that sense, is that we always prefer to plot it in log scale. Why? Because optical depth is in a way proportional to your opacity. The most important contributor to the opacity when you look at the equation, is the density of the particles, and to first approximation, density of particles falls off exponentially, right? So basically, the optical depth changes logarithmically. So if I now clear this, and I add mp.log10 here, it's going to be fine, right? And you actually see that the source function looks very similar to the temperature. And for most optical lines, it's going to be like that, because e to the hc over lambda kt is small number. So you can expand it, do some math, and you will see that source function is basically proportional to the temperature at these wavelengths. Cool. So we have the source function here. Let's now do something more. So we need to come up with a line profile, because synthesizing the spectra basically means choosing your wavelength grid and solving your radiative transfer equation on that grid. So let's say the following thing. Let's say that let's choose the width of the line. Generally, we describe a width of the line with something called Doppler width. So let's just say that it's 0.1 angstroms, e to the minus 8. And let's make the line, let's make wavelength grid. So our wavelength grid should be something like that. Lin space, lambda 0 minus dLd, lambda 0 plus dLd in, okay, let's be general and let's introduce a new number. This is number of wavelengths. I always like to make it odd. NL. So we have our wavelength grid now, and let's make a line profile, okay? The line profile describes how the line is absorbing, and usually the simplest approximation is just to make it a Gaussian. So the profile could be something like this. exp minus wavelength minus lambda 0. Don't use lambda for anything. It's reserved for something in Python that I'm still not sure what it is. Maybe people can teach us that later. I'm the worst, right? DLD, okay. Cool. Let me show you our profile now. So we're going to rerun the code. Hopefully nothing is broken. Okay, cool. Let's clear the plot, and let's plot wavelength and profile. Cool. Okay, looks like this. And basically here I only plotted the core of the line. So I think we need to extend our wavelength grid a little bit. I should have done that straight away. So let's go from center to 5 grids. Run the code again and plot this. Cool. This is more like it, right? The trick is now that what I'm going to do now is I'm going to scale our given optical depths using this quantity. So I'm going to get a wavelength-dependent optical depth. But there is always going to be continuum contribution, right? Okay, so what are we going to do is we're going to introduce a new ad hoc parameter that actually people still use in some diagnostics. We're going to call it line strength, okay? And this is going to tell you at the core of the line how much stronger line is with respect to the continuum. Let's set it to 10 at the beginning. This is actually the value that we're going to play with. We're going to play with the line strength and see how the lines look for different line strengths. So what I'm going to do now is I'm going to create no, I'm not going to create anything. I'm going to start solving the radiative transfer equation, okay? So let's do the following. What we are doing is we are calculating intensity at all these wavelengths and at all these depths. So I'm going to make an empty array for that. Okay, so I should have probably defined number of depths, but I know it's 57. This you should extract from the data, but I'm going to cheat a little bit and explicitly define it like this. So this creates ND times NL array of zeros, okay? And for every differential equation, you need the boundary condition. We are starting from the bottom, okay? Bottom means we are so deep that basically everything is very local. As soon as photon is emitted, it's immediately absorbed, okay? Which means that not only the source function, but also intensity deep in the atmosphere are equal to the Planck function, which basically means that my last intensity at all the wavelengths is gonna be equal to my last source function. And radiation is tricky because contrary to other physical parameters, radiation has direction, okay? So I cannot emphasize this enough. Intensity that we use to describe the radiation is not a vector. It's a scalar quantity which depends on spatial coordinates, but also on the angle. So when I'm looking here, when I'm looking here, let's say that I'm a point in space. I mean, I'm much bigger than a point, but okay. So if I'm a point in space and I'm looking at radiation, radiation is defined in this direction, this direction, this direction, this direction, in all the directions. It's not like a velocity that we are here and we say, okay, particles are going this way. Photons can go through each other, so intensity is defined in all directions, okay? So if, for example, density is a 3D quantity, intensity would be a 5D quantity in this case, because it depends on x, y, z, and on direction, which is determined by two angles, theta and phi, and then also on wavelength. So it's a really tricky quantity to work with, in theory. But we are not here because of that. We are here to see something else. The message was, I got carried away. Since intensity has the direction, we need to start solving our radiative transfer equation from one direction and move accordingly. So we're going to go from the bottom of the atmosphere up, and finally we are going to look at the intensity that comes out. Okay, cool. So this is our boundary condition, and now we can start solving. So what I'm going to do now is I'm going to make a for loop, which will start from the next point, go to the end. So this means it stops at 0, and this extra -1 means we are changing the direction. Okay. And what I need to do here is then to solve radiative transfer equation segment by segment, right? That's what we said. We're going to use this equation here segment by segment, okay? Cool. So what I'm going to do is I'm also going to say, okay, for all the wavelengths, now we need to solve the radiative transfer equation. Okay. We have, let's see what we have and what we are missing. We are looking for the local intensity. We have the previous intensity because we have defined the boundary condition, okay? And then it will give us the next one and the next one and the next one. So this is cool. Source function is cool. One is super cool, but delta is not cool, okay? So let's see what the delta is. And I'm going to write delta this way. So I'm going to define it explicitly here. It's easier for us. It's going to be tau continuum at the previous point, okay, minus tau continuum at the local point. So this is the difference. This is the optical path that the light has traveled, okay? But I need it at the given wavelength. So what are we going to do is we're going to multiply this by 1 plus line strength times the profile at the wavelength lambda. So what did I do here? I said the following thing. I said, I know how my optical depth behaves in the continuum, so I'm going to assume that in the line, it's proportional to the continuum plus the contribution from the line, okay? And the contribution from the line is determined by this profile, which is not properly normalized, okay? I should divide it by square root of pi, but that doesn't matter now, because we're just looking at things, times the line strength, which tells me how strong my line is with respect to the continuum. Okay, cool. So now we have the delta, and we can say the following thing. And we can finally say intensity at my point, at my wavelength, is equal to intensity in the previous point, wavelength. Actually, it's nice to define this variable, so you don't have to calculate exponent multiple times. Of course, here it doesn't matter, but it's nice practice. So we're going to do this times xpd plus source function at the local point times 1 minus xpd. Cool. This is everything. Okay? This is really everything. For those of you who know a little bit more about this, and you know for the method called short characteristics. Short characteristics is a method of solving differential equations on small segments, right? By assuming some polynomial approximation. This would be short characteristics of the 0th order. So we are assuming that things are constant on each of our segments. Cool, let's see if this works. Seems to work. And I'm going to plot wavelength versus intensity at point 0, because that's the upmost point. Please work. Ta-da-dum-dum-dum. Looks good. This is a spectral line. Okay? This really is a spectral line. Even the units are good. So I define my intensity per wavelength. Han, I think, defines it always per hertz. So it's a nice exercise for you to convert from one system to another one. But this is the absorption line, and we see how it looks like. It's stronger in the wings, okay, because the temperature is higher. It's weaker in the core because the temperature is lower there. We discussed it in previous thing. But now let's play with the line strength and see what happens there. So what I'm going to do now is this plot window is always going to stay open. I'm just going to change the line strength and see what comes up. Let's say 100, for example. I need to run the code again, plot again. What do I get now? Oh, wow. The line is stronger. Can anybody explain me now, how did we, using the same line width and same line profile, obtain the line which is objectively looking broader? Why is it so? I mean, if I ask you whether the blue line or the orange is broader, you will always say orange, right? Why is the orange line broader? It has to something to do with the equations that we were solving. Yes, Lily?
I would say because you're multiplying the Gaussian profile with the line strength, and that means you're actually taking more around the core. You're weighting more around there.
Okay, in a way I understand what you're saying. Anybody else has a different opinion? Well, the trick is that you could imagine that we are, in the first approximation, so forget the transfer problem, you could say that, okay, let's do it the proper way. If I increase the strength of the line, it means my opacity increased by a factor of 10 everywhere. It means that I'm probing now, for example, at this wavelength, it means I'm probing much higher regions where the temperature is lower. So my intensity needs to drop, okay? Or in a different way to understand this, because you would get this in the effect of pure absorption as well, is that as I'm increasing the opacity, okay, as I'm increasing the line strength, I'm increasing the opacity, I'm allowing the line wings, which are relatively poor at absorbing, I'm allowing them to become better and better in absorbing the material. Of course, this is very ad hoc explanation because it won't work into emission and complicated line transfer processes, but this is what happens. Okay, let's turn it a little bit further. The line strength, let's turn it to 1000. Now I see even broader line, and in the wings it's actually the same thing that I have told you. Opacity is higher, we are seeing the higher layers, the temperature is lower, but you see in the core something is happening. What is happening here? This small bump. Well, it's not self-absorption because it's the absorption line already, right? Self-absorption doesn't exist, actually. It's just what some people call emission lines with absorption in the core, but it's not self-absorption. It's a much more subtle effect. We can discuss that later. Yeah. So what is this? I'm increasing opacity all the time. Yes, Jonathan?
Are you sampling past the temperature minimum?
Exactly. So we have now reached high enough opacity, right? That basically what is happening is I've passed the temperature minimum. This optical depth here corresponds to the layers which are above the temperature minimum where temperature is rising. And now when I increase the strength once again, you will see that it's actually super obvious. Okay? Now I actually have emission in the line core. And this emission comes from these things.
How do they call this they give it some name, right? This happens in flares, for example.
Central reversal.
Yeah.
Core reversal, something like that.
Something
Yeah.
like that.
Yeah. I mean, but this all depends on the distribution of the source function. Really. I mean, this we could have had any form of the source function here, any physics behind it. If the shape is like this, you would get this. Simple as that. And in flares, it's probably because enhanced temperature somewhere, so you get this thing, right?
I think it's remarkable that just by using LTE.
No, but this is not true. In the real sun, the lines are not going to be like this. So if you calculate LTE sodium D lines, they're going to look like this. But it's wrong. They're not like this. Okay, and I'm just going to sketch that now. We don't have that, so I'm going to replot the source function for you people again, but in a new plot so that we don't ruin this. Just going to go plot. So remember what Phil and Han were telling us about the source functions. So this is the source function in LTE. It follows very closely the temperature. It goes down. We have the temperature minimum, which is very flat. This is why the cores of the lines tend to be very flat. Then we have the rise, and we are seeing that, okay? But in non-LTE, already around here or something like that, what happens in the source function is that we have this effect that we like to call photon leakage. And that's basically the consequence of the fact that the population levels, the population of the levels responsible for the emission mostly, are not determined by the temperature anymore, but by the density of radiation. And the higher I go, the easier it is to photons to escape, thus making the density of the radiation lower than the local Planck function. This decreases the emissivity and decreases the source function, generally. Of course, for very complicated atoms, it can be much more complicated. But for simple atoms, this is what happens. So for all these fancy-schmancy chromospheric lines that we like to investigate, calcium 2 infrared, sodium D lines, magnesium 1B, okay, H and K of magnesium and calcium are even more complicated. What happens here is that the source function doesn't go up. It just continues tanking down. And you get lines which are in pure absorption, even though there is a temperature rise. Okay? So this, you said that this is remarkable, but this is wrong. So very few lines are actually gonna follow the temperature gradient and do this.
Yeah, I mean, I'm wondering if, because I've seen that during flares.
Mm-hmm.
I'm wondering if during flares you are allowed to say, or it's valid to say that the material becomes so dense that it could be LTE in that.
Yes, that's very good. That's very good argument. Yeah, I would say so, but we should ask some flare experts. Yes. Is Adam here? No. Okay.
No, not an expert.
Yeah. But yes. Yeah, I mean, although it could simply happen that the temperature is so high that even though it's non-LTE, source function is still higher than the deeper one. So you get the emission here. Okay, and actually, if you now turn this line strength, actually, one thing that I still want to tell you is no matter how strong I make the line, far continuum is always the same, right? Because the opacity in lines falls off very, very, very rapidly, right? And this is also a reason why you should always, you should try, if you can, in your spectropolarimetric and your filter graph observation, you should try to have at least one continuum point. Is because it gives you really good constraint on how your photospheric temperatures and conditions are. Okay? Cool. So let's just plot once more for some insanely high line strength, and then we can go for this. So let's put 2 more zeros here and see what happens. No, but this is not fake. The thing is, oh, how do I go back to my old image? Okay. Let's see if this works. I actually don't know. Yeah, it works. So now the line is super strong. Why? Because the temperatures are really going high and the source function is really going high, and we are getting super, super strong line, which is mostly in emission, right? And of course, the situation is never so simple, because here I simply took an opacity and scaled it with something. So I'm always probing all the layers in a way. Okay? The only thing that I don't see is what's happening under photosphere, right? In real life, it's never really like this. All the lines have their own span of formation, right? So if I calculate something for, let's say, some strong emission line, most emission lines, when I calculate them, they're not going to have these absorption things here. Yeah, but this is just to show you how it picks up the things, and so on and so on. And in LTE, you always have this fixed depth that you can't go underneath. So you see that our lines, they're never reaching 0. Why? Because the lowest intensity that I have is the lowest possible source function in the atmosphere. I can't go beyond that. But in non-LTE, because there is the leakage of photons, then the source function can tank to much, much lower quantities, and I can get the spectral lines which are basically reaching super low levels. And you should be aware of these lines, because then it means that your signal to noise in the line core is very bad. And if you want to use something diagnosing the line core, you need to be aware that your signal to noise can change by an order of magnitude with respect to the continuum. But that's enough by now. Let's continue the discussion in coffee.
Can you do one more thing? Just change it to the wavelength of calcium K.
To change in the wavelength of the calcium K?
Yeah.
Okay. Keep everything the same.
Yeah.
Okay, so calcium K is 300, right?
39.
Okay, so we go to here. 393. Okay. Yeah, but it should be okay, huh? Yeah, so we do this. Then I think we need to clear, because we need the, okay, maybe we don't. We just can do, no, it's 2. Okay, we need to make a new figure. I already have 2, so I deleted it. Oh man, okay, then let's clear it. Okay, yeah, any questions, comments, things like that? No. So if you find these things interesting, what you can do, 2 things for like homework or like your free time on the plane or bus or something like that, is you can try to solve the radiative transfer equation in a more sophisticated way by assuming that it's actually a straight line. So that would be first order short characteristics, or parabola, that would be second order short characteristics. The other thing is you can write a code which will read this FITS file, and this FITS file is 288 times 288 atmospheres similar to this one. I mean, in the format of this one, but with different quantities resulting from an MHD simulation. So you can basically write your own simple MHD cube visualizer where you will see, then you will get Stokes cubes, and you can change wavelengths to see how this looks like. Cool. Let's go to break, and we will continue with magnetic field diagnostics after the coffee break.